Hey everybody, welcome back to Mr. A's Geometry course. In today's video, I'm going to be walking you through several examples that pertain to the first semester of geometry. If you're one of my students, the purpose of this review is to help you with recall of random lessons in random orders from the first semester of geometry. If you're not one of my students, just know that this isn't going to be in a linear order. Like this question one isn't necessarily the first thing that you learned in your geometry course. Right, so I encourage you to skip ahead or back to any questions or examples that you know that you need focus on, right? Starting off here with example one, we're reviewing complementary angles. We're asked to determine the complement of a few different angle measures. And the thing to know here is that complementary angles have a sum of 90 degrees. So if I want the complement of 14 degrees, I'm really just being asked what number plus 14 equals 90, and then I'm doing the algebra from there to solve for that measure. I can subtract both sides by 14 here to determine that the complement of 14 would be 76 degrees. For the other values, it's the same process. It's what number plus 37 equals 90. It's what number plus 61 equals 90. In example two, almost the same question. We're just asked for the supplement of angles instead. And again, the thing to remember here is that supplementary angles have a sum of 180 degrees. So instead of a number adding with 41 to equal 90, we need the number that adds with 41 to equal 180 degrees. So again, complementary adds up to 90, supplementary adds up to 180 degrees. If I subtract 41 from both sides here, I would get 139 degrees for the supplement of 41 degrees. And again, the same process to find the supplement of these other numbers. So what plus 90 equals 180, what plus 147 equals 180. That's a review of complementary and supplementary angles. In example 3, we have a proof that has to do with the triangle sum theorem. We have a triangle with two known angles, 65 degrees and 30 degrees, a missing angle there at angle B, and we're being asked to prove that this triangle is an acute triangle. Well, in order to do that, we need the measure of all the angles. So in our proof, we're first going to find out how many degrees angle B is, then we'll be able to prove that it's an acute triangle from there. Remember, the structure of a two-column proof like this is us playing lawyers, and our statements on the left are things that are true. The statements on the right are evidence that proves that that statement is true. So our first statement is that there's a triangle ABC, angle A is 65 degrees, angle C is 30 degrees. That's the given information. So the reason it's true is because it was given. 99% of proofs start this way, with the given piece of information. Next thing we have is angle A plus angle B plus angle C equals 180 degrees. Why is that true? Well, because angles A, B, and C are the three angles in a triangle, and our triangle sum theorem tells us that the three angles in any triangle must have a sum of 180 degrees. Sometimes you'll also see this called the sum of angles theorem, because the sum of angles theorem applies to any shape, like the sum of angles for quadrilaterals is that they add up to 360. So adding up to 180 is the sum of angles theorem for triangles. Just make sure you understand those really mean the same thing here. Depending on what proof you see, they may have a different option available for you to choose from there. Our next statement says 65 degrees plus the measure of angle B plus 30 equals 180. Notice that's almost identical to the equation in statement 2. Just instead of angle A, we have a 65 degrees. Instead of C, we have a 30. And those are there because we know A equals 65 and C equals 30. So we've just substituted the 65 for the A, the 30 for the C. So that is using the substitution property here on this step. Substitution property. Just going to abbreviate there. All right, our next statement here is blank. But we know the reason that it's true is because of combining like terms. And so again, if that's the evidence for this statement being true, we're just going to look at our previous equation and ask ourselves, what terms can we combine there? Well, I have like terms here, 65 and 30. Those can be combined. So we have the measure of angle B plus the combination of 65 and 30, which is 95 degrees, equals 180 degrees. Know that sometimes the combine like terms reason is also used as simplify. All right, simplify means the same thing really as combining like terms, either of those reasons could be in a proof. They would mean the same thing as what we did here, combining the 65 and the 30. Next, we have the measure of angle B being 85 degrees. Well, that's solvable from this equation. If I want angle B alone, I can move that 95 to the right side of the equal sign by subtracting both sides by 95, and that would give me 85 degrees for B. So as I said, that's using the subtraction property of equality, because we're subtracting from both sides using the subtraction property of equality there for that statement. And finally, the proof is ending with what we're asked to prove. Notice it's the same thing. We have to prove ABC is an acute triangle. That's our last statement. This should always be the case for every proof you see. That's our last statement. And we do have the evidence of it now, because an acute triangle, by definition, is a triangle where all three angles are acute. They're all less than 90. We already knew that A was less than 90 and that C was less than 90. We just proved that B was less than 90. So by definition, this has to be an acute triangle. All three angles are less than 90 degrees. So this is just true because of the definition of acute triangles. That's example 3, that proof done. In example 4, we're providing some counter examples for conjectures. A conjecture is just a statement, an unproven statement. So if we're providing a counter example, that means our conjecture is false, and we just need to give an example of why it is false. For example, I'm going to start with the easiest conjecture here, which is B. It says, if you live in the USA, then you live in Florida. Well, for anyone in Florida, that conjecture is true. By anyone that lives in any other state, it's a false conjecture. If you live in the USA, you could live in Georgia. So Georgia is a counter example that proves that that statement is not true. So let's look at the rest of our conjectures. In A, it says the product of two numbers is always greater than either number. That is not true anytime you multiply a number by 1, by 0, or by a negative number. For example, if I do 6 times negative 3, I get negative 18. And negative 18 is not greater than 6, so that proves that that conjecture is false. Option C says if two angles are complementary, then one of them is less than 45 degrees. We've already discussed complementary means that they add up to 90 degrees. And we have one example that proves this statement is wrong, and that's if you have two 45-degree angles. 45 plus 45 equals 90. Two 45s are complementary, but neither is less than 45. That's a counter example. And statement D says if an angle is bisected, then the resulting angles must be acute. Remember, to bisect means to cut in half. If you bisect a straight angle, then you will get two angles that are not acute. As a reminder, a straight angle is an angle that looks like opposite rays. It is 180 degrees. If I cut that in half, I'm going to get two right angles. I'm going to get two angles that are 90 degrees each, and those are obviously not acute angles. Acute is less than 90 degrees. Our next 3 examples here are all tied together, all involving transformations on a graph. We have a pre-image here, triangle ABC. A is at 0, 0, B is at 3, 3, C is at negative 3, positive 3, and we're being asked to reflect this shape over the x-axis. Remember, we want to think of reflections as flips, and the line we're being asked to flip over is the most important thing to identify. So the x-axis in this example, remember, is our horizontal axis. It's that one right there that I've highlighted in green. And our idea is to figure out how far away our points are from this line and flip them the same distance to the other side of the line. For example, point B we can count is 1, 2, 3 units away from the line of reflection right here. So its image will be the same distance on the other side, 1, 2, 3 units. So right here at positive 3, negative 3 would be the location of B prime. We can do the same thing with C. We have 1, 2, 3 units away from our x-axis. So 1, 2, 3 units to the other side will be C prime at negative 3, negative 3. Now what happens with point A? Any point that is on a line of reflection will remain on the line of reflection. So that means that A prime is located at the same location there. And we can then connect our vertices, and this would be our image of ABC prime. Remember, reflections will always create symmetry like this on either side of the line of reflection. This was reflecting by hand. We can do the same thing by memorizing a function notation rule. Anytime we reflect in the x-axis, this rule applies. Our x-coordinate stays the same, but the sign on our y-coordinate changes. For example, b was at +3, b prime is at +3, -3. So the x-coordinate stayed 3, but the y-coordinate went from positive to negative. So that rule will allow you to reflect any point over the x-axis. If you memorize it, you don't have to do it by hand. Let's look at our next transformation on example 6. Again, we have the same pre-image. This time though, the directions are telling me to rotate this thing 180 degrees. All right, so 180 degrees. I've made a second graph over here so I can show you a physical rotation here on screen. And notice that it says to rotate clockwise, although technically the direction of a rotation here does not matter. Let me make sure that I do not get all this extra stuff on my screen grab here. The direction of this rotation doesn't matter because 180 degrees, you're gonna end up upside down no matter what. I just put the clockwise there to show you here of my software. As I rotate, I can rotate to the right, which is clockwise. So this is gonna be 90 degrees. That's a quarter of a turn of rotation to the right has occurred over here. And here is gonna be another rotation of 90 degrees to the right, and that's a total of 180 degrees. So this shows us where the image of this triangle should be. So this is how we can rotate by hand. If you have this on paper, you can physically just turn it upside down. And the locations of your points now are where your image should be located. For example, A is still at the origin in the middle, so that I know that A prime here is going to be in the same exact location there at the origin. To get B and C, I'm just counting how far away those points are from the origins. For example, to get to B, I would go to the left 3 and down 3 to get to point B. So I memorize that pattern, left 3, down 3. When my paper is normal, I go from the origin, left 3, down 3, and there is the location of B prime. We do the same thing for C. From the origin, that's right 3, down 3 to get to point C. So when I bring my paper normal, I go right 3, down 3. That is where C prime should be. So doing rotations by hand allow you to see where your image should be graphed if you didn't turn your paper. That's where it should be, and this is where our image is. Now, question 7, actually before I go on to question 7, let me tell you, there is a rotation rule that you can apply for 180 degrees. There is a function notation you can follow. So if you don't want to do it by hand, you can instead memorize the rule that xy becomes -x, -y. You just change the signs of your coordinates. All right, for example, point B was at +3, +3, it ended up at -3, -3. Point C was at -3, +3, it ended up at +3, -3. So you just change the signs of your coordinates to do a 180 degree rotation. You can memorize that rule. You can do this without having to turn your paper upside down or anything like that. Now, example 7 is asking us to take a look at our images in questions 6 and 5. So there's our image from 6, ABC prime. And then in our previous example, we see it's almost exactly the same. Matter of fact, if we don't look at the coordinates, it is exactly the same. All the points are plotted in the same locations. The question here is asking us to notice any differences. And the differences come from points B prime and C prime. Notice B prime is down here in quadrant 4 and C prime is in quadrant 3 for the reflection. However, in the rotation, B prime is in quadrant 3, C prime is in quadrant 4. So again, notice C prime was in the bottom left on the reflection, C prime is in the bottom right on the rotation. So the reason that I'm showing you this example or asking you what are the differences here is for you to be very careful when you're trying to describe transformations that happen. Because at first glance, we could easily look at this and say that a reflection happened because there's symmetry over the x-axis. But if we actually look at our coordinates, we realize, okay, B didn't actually flip over the x-axis. It ended up over here in this quadrant. This is a 180 degree rotation. So the differences are the locations of B prime and C prime in different places when we rotate 180 versus when we do a reflection over the x-axis or the y-axis. In example 8, we are reviewing counter examples again. We're told if a number ends in a 6, then it is evenly divisible by 4. Remember, a counter example is something that proves a statement is false. And so we're going to evaluate the 5 options that we have and circle the ones that would prove this conjecture is not true. So any number any number ending in 6 is divisible by 4. 36 ends in 6, and you can divide that by 4. 36 divided by 4 equals 9. That does prove that conjecture. It supports the conjecture, right? 16 is also divisible by 4. If we divide 16 by 4, we get 4. That does support our conjecture. When we divide 66 by 4, we're going to get a decimal though, which I do not recall off the top of my head. So really quick, 66 divided by 4 is 16.5. That is not evenly divisible, so that is a counterexample to this conjecture. This is not evenly divisible by 4. It doesn't support it, right? When we divide 76 by 4, we get 19. That is a whole number that is evenly divisible. That supports the conjecture. When we do 46 divided by 4, we get 11.5. That is not evenly divisible. That does not support it. So 66 and 46 are counterexamples to this conjecture. We're on example 10 next because I forgot to put an example 9 on this review. It's my bad. And again, we have a proof here. Remember, we're going to be lawyers. We're going to say things that are true in our statement column, and then we're going to provide evidence that proves that they're true in our reasons column. We have a triangle again with some given information for our 3 angles, and we're being asked to prove that angle C is 72 degrees. So we start off with these statements, which is the given information in our figure. So the reason this is true, the evidence for it, is it was given. Okay? In our next statement, we have the sum of angles theorem being the reason that the statement is true. Well, the sum of angles theorem for a triangle is that all the angles add up to 180 degrees. And you could argue what we need to put here is that angle A plus angle B plus angle C equals 180, that the measure of all those work here. However, with this one, I don't have a step next that uses substitution to sub these values into it. It just goes straight to combining like terms, and I don't have like terms in this equation. So I actually need to be writing this with the values plugged in. So angle A is 38 degrees, angle B is X, angle C is X plus 2. Those add up to 180 for my sum of angles theorem here. My next statement can only be true because I combine like terms. So that means we need to look at this equation and combine the like terms. For example, we have X plus X. That gives me 2X's, right? We have 38 and 2. Those are like terms. Those combine to give me positive 40. That's combining our like terms. Our next statement must be true because we subtracted. So the thing that I can subtract there is the 40. If I want 2X alone, I can subtract 40 on both sides. And if I do that, I subtract 40 on the left, the 40s cancel. If I subtract 40 on the right, I would get 140. So my result would be 2X equals 140. My next statement can only be true because of division. Well, what I can divide here is a 2 on both sides. If I divide this side by 2, they cancel. If I divide this side by 2, I get 70. So the result there would be X equals 70. This is true because of the division property. I can divide both sides by 2 to get this value. Our next statement must be true because of substitution, and what we will be doing is substituting this 74 and X in a different equation, and that equation will be for angle C, because what we're being asked to prove is that angle C is 72 degrees. So we need to plug that 70 into that expression. So the measure of angle C equals X plus 2. Again, that is something that was given to us. So we're just going to substitute the 70 for the X in that equation. So it's going to equal 70 plus 2. And then we can end our proof with the way all proofs end. Whatever it's asking us to prove must be our last reason. The measure of angle C is 72 degrees. Okay, that is true because of simplification, which is just also combining like terms. It could also be a word that goes there, right? 70 plus 2 gives me 72 degrees. That's this proof done. In our next few examples, we're going to be reviewing congruent parts or corresponding parts from congruent figures. So here we have a figure of 2 congruent triangles. You notice all 3 angles have the same amount of arcs. We have all 3 sides with matching arcs
on them to give us congruent triangles, and we're just matching the corresponding pieces. So angle A is congruent to the angle with the same amount of arcs as angle A. Angle A has 2 arcs, angle D has 2 arcs, so angle A must be congruent to angle D, right? Angle B has 1 arc, right? So that angle must be congruent to the angle that has 1 arc, which would be angle E. Those are corresponding and congruent parts. So angle B has to be congruent to angle E. Angle C has 3 arcs. That's got to be congruent to angle F with 3 arcs. So angle C is congruent to angle F. Now we're looking at sides. So this is a segment symbol. These are the sides of our triangle. Side AB has 1 dash on it. That would match side ED with 1 dash on it. So side AB corresponds and is congruent to side ED. Was that side ED? Making sure I didn't make a mistake. BC, that side has 3 dashes. That will be congruent to side EF with 3 dashes. And then lastly, we have side AC, which has 2 dashes. That'll be congruent to DF with 2 dashes. AC congruent to DF. So this example is really just our visuals. Do we understand our congruent marks between 2 figures to know which sides and angles correspond with each other? Now, to further our knowledge of that, we have to be able to evaluate congruency statements. So notice these figures don't have any marks telling us which pieces are congruent. However, this congruency statement tells us which pieces correspond and are congruent to each other. So we need to solve for x and y. That first requires us to locate and figure out where those variables are located in our figures. For example, I see an x right there. That's inside my figure. That's an angle. Which angle? Well, it's in the corner where the D is, so it's angle D. And this statement tells me that angle D is congruent to angle K because they are in corresponding positions of the congruency statement. So because the shapes are congruent or equal in measure, angle D must be equal in measure to angle K. Angle K is 25x minus 8. Therefore, to solve for x, I'm setting those 2 things equal to each other in solving. So we have 20x plus 12 for angle D. That must be equal to the 25x minus 8 for angle K. And from there, we can do algebra to solve for x, which I'll go over with you. We have x's on both sides. I don't want that. I want x's on one side of the equal sign. So I'm going to subtract 20x from both sides. That'll cancel the x's on the left and leave me with just a 12. On the right, we have 25x minus 20x. That gives me 5x's, and we still have the minus 8. Now that all the x's are on the right, I want to keep them on the right and get rid of everything else. So I'm going to move that minus 8, and I do that by adding 8 to both sides. So that gives me 20 equals 5x, and lastly I can divide both sides by 5 to get x equals 4. Right, now we're on to solving for y. And again, that requires me to first locate where y is. Well, here's a y. That's outside my figure. That's a side. Which side? It's on the side between G and F. That's side GF. My congruency statement has G and F as the last 2 letters. That'll correspond with the last 2 letters here, which are N and M, which is this side over here. So these values must be equal to each other because they're in corresponding positions on congruent figures. So 2y plus 3 has to equal 4y minus 29. So 2y plus 3 has to equal 4y minus 29. Let me make sure I didn't mess anything up there. 4y minus 29, 2y plus 3. Perfect. Doing our algebra now to solve. Again, same idea. I want y's on the same side. I like moving the smallest amount of y's. Those cancel, leaving me with 3. I got 2y minus 29 on the right. I get 2y alone. By adding 29 to both sides, that gives me 32 equals 2y. Then I can divide both sides by 2 to get y equals 16 in this example. We got one more example here involving a congruency statement. We're told triangle ABC is congruent to triangle LTR. We're given a measure for A, B, and C, so we know all the degree measures for triangle ABC. We are given a variable on angle T, and we're asked to solve for the x, that variable at angle T. Well, again, the key is reading the congruency statement. That statement tells me what angle is congruent to T. T is in the second position. that must correspond with angle B, which is in the second position for this triangle. Because the triangles are congruent, it means equal in measure, those angles have to be equal. So angle B is 60 degrees, therefore my angle T must also be 60 degrees. So angle T is 5x, angle B is 60, those need to be equal values. 5x must equal 60. We can divide both sides by 5, and x would equal 12 degrees in this problem. A little follow-up there for classification. We're asked, are these triangles acute, right, or obtuse? Well, if they're congruent, that means all the angle measures are the same. So both triangles have 50, 60, and 70 degrees. All of those are acute angles. Therefore, they are both acute triangles. In example 14, we are identifying the types of transformations that have occurred on a graph. In our first example here, we have two triangles that look like they have symmetry. Anytime we have symmetry, our first guess should be reflection. And when we're guessing reflection, we really just need to identify if there is a line of reflection on a graph. Right? For example, lines of reflections always connect the midpoints between an image and a pre-image. So if we're saying B and E correspond with each other, the midpoint would be right here on the y-axis. If C and F correspond, the midpoint halfway would be right there, again on the y-axis. If A and D correspond, their midpoint would be here at 0, -1, which again is on the y-axis. So that means there is a line of symmetry or a line of reflection, which means we can describe this as a reflection. This is a reflection. Notice this question is not asking us for any rules or anything. It's just saying what type of transformation. This is a reflection. It's a flip. Okay. In our next example, we have a slide. Our points here, I know it's kind of hard to see. This is a pre-image ABC, and this is A prime, B prime, and C prime. So all of our points have shifted down in this direction. And anytime we're sliding, we have a translation. One key to know that a translation has happened is that we get parallel parts when we translate. And so these corresponding sides, AB and AB prime, appear to be parallel to each other. Same thing with AC and AC prime appear to be parallel to each other. A little bit harder to see with BC and BC prime. They'd also be parallel to each other, never intersecting. That's a translation. And our next one, the only transformation we've learned of that makes a shape bigger or smaller is a dilation. That should be an easy one to spot. Dilations are going to make enlargements or reductions. Okay, and our last one, we have a turn. All of our points on our pre-image ABC have turned this way around the origin, and our turns are always rotations. One other indicator that you have a rotation is all of your points have moved the same amount of quadrants. All of our points on our pre-image here are in quadrant 2. They've all traveled one quadrant over clockwise. You could also say they went 3 quadrants counterclockwise. The point is they moved the same amount of quadrants. That's also an indicator that a rotation has occurred. Right now, our follow-up question to this, on 15, it says, which of these transformations results in congruent figures? So this is a very important idea. Remember, 3 of these are called rigid transformations, which don't make a shape bigger or smaller, just moves it somewhere else. So a reflection doesn't make a triangle here larger or tinier, it just flipped it somewhere else. A translation didn't make the figure bigger or smaller, just slid all the points the same distance and direction somewhere else. The rotation did not make a shape bigger or smaller, just turned it somewhere else. The dilation does make a shape bigger or smaller. Therefore, this does not result in a congruent figure. This is not a rigid transformation, the rest are. So to answer this question, which says which ones resulted in congruent figures, well, the congruent figures were all the rigid transformations. That is the reflection, the translation, and the rotation. And then the non-congruent transformation is the dilation, because that made the shape bigger or smaller. They wouldn't be equal in measure anymore. 16 through 18 is a series of exterior angle theorem problems. We're talking about triangle measure here with our angles. We have a triangle with one side extended, creating an exterior angle. And the rule here is that exterior angle is equal to the sum of the non-adjacent angles. So this angle is adjacent to x, it's right next to it. These, though, are non-adjacent. They're far away from that x. And so the rule is that angle equals the sum of these. So x will equal 75 plus 36. X equals 75 plus 36. We would get 111 degrees in this example. This same idea will apply to our next two examples as we see similar positioning of given angles. Here there's x's everywhere, and we tend to freak out about that. But we just need to try to recall one theorem, one relationship at a time. There's a triangle with a side extended, creating an exterior angle. And again, that will always equal the sum of those non-adjacent angles that are farthest away. So 5x plus 13 will equal 4x plus 2 plus 2x minus 9. Because we're adding, these parentheses don't really matter, right? If we were subtracting or doing anything else, it would be important. But when we're adding values, parentheses isn't really going to come into play. Right, we have a lot of algebra to do here. We have like terms to combine, but none on the left. The 5x and the 13 need to stay the same. On the right, we have 4x plus 2x. Those need to be combined to 6x's. We have a positive 2 and a minus 9. Those combine to a negative 7. Right? Now I have x's on both sides, and I don't want that. I want them on the same side. I like to move the smallest amount of x's, so I'm going to subtract 5x from both sides to get all my x's on the right. Those 5x's cancel to leave me with 13. On the right, I have 6x minus 5x, leaves me with 1x. I still have the minus 7. Now I can get x alone by getting rid of that minus 7 by adding it to both sides. Those cancel on the right, leaving me with just x. 13 plus 7 is 20. X is 20 in this example. In our next example, we have a very important example, okay? In a lot of standardized testing, a lot of testing that you might be going through as a geometry student, you will have examples that ask you to solve for x, but you will also have plenty that ask you for something other than a variable. And unfortunately, a lot of students tend to stop short sometimes. So make sure you're being careful in answering the question that's being asked. But first notice again that we have the positioning for our exterior angle theorem. 20x is on the outside. That's got to equal the sum of these angles furthest away. So this will start by us solving for x with that same theorem applied. 20x equals the sum of these non-adjacent, 7x plus 5 plus 60. And again, we're doing algebra to solve. I have like terms here on the right. I'm going to combine those. 20x still on the left, 7x still on the right. I got 65 over there when I combine 5 and 65. Now I can get all x's on the left by subtracting 7x from both sides. That gives me 13x on the left equal to 65. And then I can get x alone by dividing both sides here by 13 to get x equals 5. Which again is not the answer to the question being asked. I need to find the measure of angle BCD, which is something some students tend to struggle with. Where is angle BCD? Well, remember, angles are located where the middle letter of their name is. That's the vertex of the angle. That's down here at angle C. That's 7x plus 5. You can also kind of do this highlighting trick. If you go from B to C to D, that highlights the sides of the angle. The angle itself is what's inside. So you think of angles as alligator mouths. The angle itself is what the alligator's eating. It's the 7x plus 5. So the measure of angle BCD equals 7x plus 5. I know that x is 5, so I can substitute that in here and solve. 7 times 5 plus 5. 7 times 5 is 35. 35 plus 5 gives me a measure of angle BCD that is equal to 40 degrees in this example. All right, next up we have a few constructions to review, which I'm going to do my best to show you with my big little compass here that I have on the TV screen. Even though I won't actually be setting this or making any marks with this, I'm going to be doing it on my screen over here to show you. And what we're doing here to start is copying a segment, meaning I need to make a segment that is congruent to CD. All right? In order to do this, we have a first step, and really it's the process of steps that matters here. Because when you're assessed on any standardized testing, you're generally not going to be given a physical compass to do it, so it doesn't truly matter that you can do it by hand. What matters the most is that you can recognize and understand the steps to doing a construction. Okay, so our first step can actually be one of two things here. Some sources will tell you your first step is to start with an endpoint on a new segment. All right, and let's say if we're matching this, we can call it C prime if we want to. We can call it whatever we want. I'm gonna call this point A, and that's gonna be my point C for this segment. right? Some other sources would say that you need to start by just drawing a long segment like this and then putting an endpoint on it, right? It doesn't really matter which comes first, the segment or the endpoint, as long as you end up with this. Notice I clearly drew this longer than CD for a specific reason. What I'm going to be doing now is measuring with a compass the distance from C to D, like so. And then I would keep that setting on my compass, carry it down here, and then use it to make a mark there. Ooh, that worked. Make a mark there across my segment. And then where that intersects would then be the end point of my segment, and these pieces would be congruent to each other. That's how we copy a segment, right? Let me show you one more time for clarity. There's the segment AB. Again, depending on the source of your learning of copying a segment, we could start by drawing a new point A, or we could start by making a segment that's longer and then putting an endpoint on it. Doesn't really matter which of those comes first, as long as we get the rest right. We're going to put our compass on this segment. We're going to measure how long it is. We're going to carry that measurement over here, and then we're going to swing an arc across. And again, that intersection right there be my other endpoint, and those segments would be congruent to each other. That's copying a segment. Oh, I got some more copying segments here. Again, just to hammer it in, right? We got a segment clearly longer than GH. I'm gonna put any endpoint I want over here. I'm gonna call this point A. My compass is gonna measure from G to H. I'm going to carry the same exact setting down here, and boom, right there is going to be my other endpoint, and now those segments have to be congruent to each other. Notice I don't have to draw it like parallel to the one that's given, I just need it to be the same length, right? And then we're going over here to this last one. Again, we have a segment. I'm going to draw something clearly longer. I'm going to call my endpoint whatever I want to. I'm going to use my compass to measure my original segment, and I'm going to carry that measurement over to copy that segment length over here. That segment CD would be congruent to AB. Again, that's copying a segment. I think that was the last one. It is. Next up, we have a series of weighted average examples. Before I teach you how to solve for the weighted average of this number line here, though, I'm just going to remind you how regular average works. Let's say I wanted the average of 3 numbers. I'm just going to make them up 5, 10, and 20. What I would do is add them together and then divide by the total amount of values that I've added. 5, 10, 20. That's 3 values. So I'd be dividing by 3. Then again, I would add those values up. That would give me 25. I would divide by 3, and then I would get my average. That would be 8.3 recurring in that example. We have a similar thing happening with weighted average. The only difference is, instead of having 1, 5, 110, and 120, when we add weights, we may have multiple of a value involved, right? So we'll see exactly how that works here on our number line, right? So we have a 0 with a coordinate above it. We have a 1 with a coordinate, 2 with a coordinate. We have 7 with 3 values that are given to us there. Here's how this works. There is a 0, right? 1x for a 0 gives me 1, 0. And then because we're doing average, we're going to add them, just like we did before. There's 1, 1. We have a 1. There's 1, 2. So there's 1, 2. And then notice there's 3 x's above a 7. So that means the 7 has a weight of 3, which means I would have 3 7s. So there's 1, 2, 3 7s. And then notice here, what I would divide by now isn't the 4 numbers that have x's on them. It's the total number of values. 1, 2, 3, 4, 5, 6. I would be dividing by 6. Oops. Be dividing by 6. And again, I can just calculate from here. If I add all those numbers up on top, I'm going to get a sum of 24. When I divide 24 by 6, I get a weighted average of 4. Now, what's very important is that weighted average can sometimes not look as pretty as this, where I get a value that's not a whole number, right? Or where I get weights that are not whole numbers. And so for that reason, I want to show you a better way to do this calculation that will help you no matter how complex your weighted average is. Instead of writing it this way, where I did 7 plus 7 plus 7, and just 1, 0, 1, 1, and so on, we are going to take the values, so the coordinates on our number line that have weights, we're going to multiply them by their weights. And you'll see how this is going to give me the same result in the end here of 4. So the 0 on the number line had 1x above it, so that means it has a weight of 1. We're going to multiply it by its weight of 1. We're still going to be adding since we're doing average as we did. The 1 on the number line had a weight of 1, so I'm multiplying it by 1. The 2 had a weight of 1, so I'm multiplying it by 1. So again, I'm taking each coordinate and multiplying it by its weight. So that means when I add for our 7s here, I'm adding a 7 multiplied by its weight of 3. And on the bottom, what I'm doing is I'm getting the sum of the weights. So I'm not going to change things here and divide by a different number. It's still going to end up being 6. You might be confused though because you see like 4 terms here, 4 expressions as we go across. What we want on the bottom though is the sum of what's in parentheses. So 1 plus 1 plus 1 plus 3, and we want to write it out like this and do our calculations afterwards. And you'll see why that's valuable in future examples, okay? So then we can calculate. 0 times 1 is 0. 1 times 1 is 1. 2 times 1 is 2. 7 times 3 is 21. When I add all the numbers in my denominator, 1 plus 1 plus 1 plus 3, I get 6. When I add all the values on my numerator, I get 24. 0 plus 1 plus 2 plus 21 is 24. And then I'm dividing 24 by 6, just like I did previously to get my weighted average of 4. Now, I know some of you are asking, why would I do all this when that was a lot easier at the top? Well, that's because of the next example that we're going to go over here, where 10 has a weight of 2/5 and 45 has a weight of 3/5, and we need to calculate the weighted average, right? So this cannot be written the way that we did this up here because of the weight. I don't have just one of the numbers, I have a fraction of the number. This is where writing and setting up our weighted average this way is going to be useful for us. So again, let's follow. We're taking the coordinate, the value of 10, and we're multiplying it by its weight. In this case, it's a fraction of 2/5. We're adding that to our next coordinate, 45, multiplied by its weight. Those are our only coordinates. Remember, we're dividing by the sum of our weights. That's adding the numbers that are in parentheses here. And then we are calculating, right? If we want to do 10 times 2/5, we'll do 10 times 2 divided by 5. We could leave that as a fraction. If we do 10 times 2, we get 20. We could leave it as 20 over 5. But if it's going to give us whole numbers throughout, we might as well write the whole numbers down. 10 times 2 divided by 5 gives me 4. I'm also going to get a whole number here. 45 times 3 divided by 5 gives me 27. And then on the bottom, we have 2/5 plus 3/5. That gives me 5/5. Then we can continue calculating. 4 plus 27 is 31. 5/5 is just 1, right? So it's 31 over 1. And that division gives me 31 as my weighted average for these values. So again, we're going to take our coordinates, multiply them by the weight. We're going to do that every time because sometimes we'll have fractions, and that we must do it that way when we get our fractions. Good news with the fractions though, on our denominator, we're always going to get a sum of 1 if our weights are fractions. We can't be evaluated here in high school geometry with fractions that don't add up to a whole number. We need to get a sum of 1 there on our denominator. Let me give you another example of that here. Q on this number line has a weight of 6/8. Well, Q is -4. So that means my -4 is going to be multiplied by 6/8. My y has a weight of 2/8. My y is +4. So I'm multiplying that by its weight of 2/8. And again, I'm dividing that by the sum of these weights, 6/8 plus 2/8. And again, I'm going to evaluate from here and multiply. I'm doing -4 times 6 divided by 28. -4 times 6 is -24. Divided by 8 would give me a product of -3. 4 times 2 divided by 8. 4 times 2 is 8. 8 divided by 8 gives me +1. So I got +1. On the bottom, 6/8 plus 2/8 gives me 8/8. Remember, we're always going to get 1 on our denominator there when we have fractions as our weighted average. 8 over 8 is 1. -3 plus 1 on top gives me -2. 8 over 8 again gives me 1. And when I divide anything by 1, it's equal to itself. I got a weighted average of -2. In the last weighted average example here, I'm going to give you, we have a little tricky outcome with our fractions, but we're setting it up the same way. My coordinate of 18 here has a weight of 1/5, so I'm multiplying by 1/5. My coordinate of 4 has a weight of 4/5, so I'm multiplying by 4/5. and I'm dividing that by the sum of the weights. 1/5 plus 4/5. Here's where things are a little tricky. When I do 18 times 1 divided by 5, I don't get a whole number. It's not really an ugly decimal either. That would be, 3.6 I think is the result of that. But I don't want to write decimals in the result that the fraction answers that I get here give me a whole number in the end. So instead, I'm going to leave it as a fraction by only multiplying by the numerator. 18 times 1 will give me 18 as the numerator over 5. So 18 times 1/5 will give me 18/5. And then I'm going to do the same thing with 4 times 4/5 because that also doesn't give me a whole number. 4 times 4 is 16. 16 divided by 5 would again be like 3.2. Right? I want to leave this as a fraction, so I'm only doing the multiplication by the numerator. 4 times 4 is 16. So I get 16/5 when I do that multiplication. On the bottom, 1/5 plus 4/5, all that's going to stay the same as it was in previous examples, gives me 5/5. And from here, we're starting to evaluate more. Now what I'm doing is the same thing as adding these fractions up here. 18 plus 16 is going to give me a total of 34/5 up top. On the bottom, 5 over 5 is 1. I know that looks kind of like a super fraction as I write it out here, okay, but it's just a numerator of 34/5, a denominator of 1, okay? And now we can evaluate what's going on up here on the top, the 34 divided by 5. Because we're saving that division for the end, we're able to get the most accurate answer here, whereas if we wrote down decimals or potentially rounded anything before this, our answer could be off a little bit. That's why we're doing this with fractions all the way through. 34 divided by 5 is 6.8, right? We can leave it as 6.8. We can leave it as a fraction. We know anything divided by 1 is equal to itself. So it's possible if we're doing multiple choice on a standardized test that is our answer, because again, anything divided by 1 is equal to itself. Or we could look for that decimal. Again, let me just confirm here that 34 divided by 5 is 6.8, and it is. Right? Several weighted average examples there. Again, the key is that setup, taking a number, multiplying it by its weight. Again, we have that rare example where sometimes we're not going to get a whole number in the end, which is where it's going to be good to not divide that fraction's denominator until the end to get the most accurate answer. In example 25, we have some error analysis. These are my favorite types of problems. We got Susie saying that the transformation shown on graph here can be described as AB transforms into negative AB, and we have to describe the error that's involved. In order to do this, we need to understand what this is function notation. It's describing the change of coordinates from the pre-image to the image. So let's identify. The pre-image is the one without apostrophes. That'd be this triangle. This is the image, the new one. And in order to find the error in Susie's function notation, we need to determine what the correct function notation is. So we're going to look at points and evaluate them. The best points to evaluate for function notation are ones that have different values for their coordinates and possibly different signs. Okay, for example, B is located at 1, 1. That's the same value for the X and Y and the same sign. A is located at 3, 4. That would be a better point for us to evaluate. So point A on our pre-image is located at +3, +4, and it transforms into A prime. And we can see that A prime is located at +3, -4. And we can evaluate from there what has happened and changed between our coordinates. Now, one thing that might be a little tricky here is the use of A and B when typically we use X and Y in function notation. So I'm going to stick with that. I'll also show you what it looks like with A and B. So we start X and Y, +X, +Y, and it becomes the same thing for our X coordinate. The +3 stays a +3. So in our function notation, the X coordinate needs to stay the same. The Y coordinate, though, goes from +4 to -4. So that +Y, we need to show changes its sign and becomes -Y. This is the correct function notation. In AB form, if we just substitute those for A's and B's, again, the first coordinate, the A, stays the same. The second coordinate, the B, changes its sign. And we can see now where Susie's error is. She changed the sign of the X coordinate instead of the Y coordinate. So Susie's error is that she changed the sign on the wrong variable. You could word that however you want in your own words, or you could just show the correct function notation would be enough for me of explaining Susie's error.
In example 26, we're performing a 180-degree rotation clockwise. Again, direction doesn't matter for 180 degrees because if we go clockwise or counterclockwise, we're still going to end up upside down. I have the pre-image here duplicated to the right to show you this rotation. So I'm going to go 90 to the right, that's clockwise. Another 90 to the right would be 180 degrees, which would look like this. You can do this by hand with your own graph paper. If you're doing 180 degrees, just turn your paper upside down, and then you'll see where your coordinates should be, assuming that you didn't turn your paper. So point A from the origin is left 2 and up 3. You can memorize that pattern, turn your paper back normal, and then graph that pattern. From the origin, left 2 and up 3, that would be the location of A prime. And you go back and do this for each point. To get to point C here from the origin, I would go to the right 8 and then up 3. I remember that pattern, go right 8, up 3, there's C prime. Do the same thing for point B. I'd be going right 6, up 7 to get to point B. We follow that same pattern to get to B prime, and we have triangle ABC prime after 180 degrees of rotation here. All right, our next example, or exercise here asks us, would our image be any different if we rotated counterclockwise instead? And I will show you the proof here that it does not matter which way we rotate. And bring this back normal. Okay, so again, there's our pre-image down here. If I had to go counterclockwise instead, that'd be rotating to my left 90, and then another 90 to the left. And again, we see it's in the same exact location, no matter which direction we go. Our next few examples require the use of the distance formula to find the distance between 2 points. Right, the distance formula is, I'm gonna put it on screen here for you and keep it here. It's x2 minus x1 squared plus y2 minus y1 squared. Here in Florida, the distance formula is given to you on the reference sheet when you take your standardized testing, so this doesn't have to be memorized. In order to use it though, you need to make sure that we're careful. We label our points x1, y1, and x2 and y2, and we plug them in carefully into that formula. So x2 is -4 minus x1, which is +2, squared, plus y2, which is -11, minus y1, which is -3, squared. From there, we can clean up any signs or do those operations in the parentheses with our order of operations here. So -4 minus 2 is -6. -11 minus -3 is really -11 plus 3, which is -8. Next, we need to square. -6 squared is 36, -8 squared is 64. I'm gonna move over here because I'm running out of room. When we add those together, we get the square root of 100, which happens to be a whole number, which is 10. So the distance between that set of points, 10 units apart. We're gonna be doing the same exact thing for this set of points. So we're gonna label x1, y1, x2, y2. And we're gonna plug those into our distance formula here. Right, so we have x2 minus, minus x1 squared plus y2, which is 0, minus y1, which is -2 squared. Then we're following the order of operations here to solve. 2 minus 1 gives me 1 in that first parentheses. 0 minus -2 gives me 2. Then we're doing exponents. We're squaring. 1 squared gives me 2, 2 squared gives me 4. We add those together, coming over here, we get the square root of 5. And typically with distance formula, I like leaving answers exact, especially if we're only doing the distance formula. This is an exact answer. These points are the square root of 5 units apart from each other. If we needed a rounded value here, then we can do that and round to the nearest tenth, or we could follow any rounding directions that are given to us on any assessment. That would be about 2.2 if we're rounding to the nearest tenth here for those. Example 29 is the same thing. Even though it doesn't say here, find the distance between 2 points, it's asking us to do that because the length of this segment is the distance between point A and point B. In order to do this, we need to know those coordinates. From the origin, A is left 2 and up 3. That is the location -2, +3. From the origin, point B is right 1, down 1. That's +1, -1. And again, we're going to label those.
and we're going to carefully plug them into our distance formula. So square root of x2, which is 1, minus x1, which is negative 2 squared, plus y2, which is negative 1, minus y1, which is 3 squared. And we're doing our algebra from there, order of operations. 1 minus negative 2 is positive 3. Negative 1 minus 3 is negative 4. When we square these values, 3 squared gives me 9, 4 squared gives me 16. We add those values together, we get the square root of 25, and in our calculator we can determine that that is a whole number, which is 5. So distance formula, very important. In example 30, we have multiple variables to solve for on parallel lines. So this is a great review of the angle pairs that are created on the interior of parallel lines, because all these are in between our lines here. I'm going to show you one angle pair at a time, and I'm going to start with A. All right, so we have parallel lines here. This transversal and extended matters here. And the pair that we're specifically going to be looking at here to solve is the 58 and the A. I'm going to show you what I've just highlighted here separate so that it sticks out for you. We got 58 here, we got A here on parallel lines. That is alternate interior angles. We learned in Unit 3 that alternate interior angles are congruent when they're on parallel lines. Therefore, A has to equal 58 degrees. So no algebra is required there. It's just recognition of that angle pair on parallel lines being congruent to each other. We're going to have this same exact angle pair looking at this transversal over here with the 48 and the B. And again, in case you can't see it, I'm going to draw that separate, where we have the 48 right here, the B right here. That is another pair of alternate interior angles that again have to be congruent on parallel lines. So B must also be 48 degrees. We can absolutely solve for C next. We can do it a few ways. We can look at these three angles that are on one side of a straight line. They have to be supplementary. So that C along with the 58 from A and the 48 from B have to add up to 180. We get the same math when we look at triangles, which is probably more recent for you, maybe a little bit easier to determine there. Triangle sum theorem. We know that C plus 48 plus 58 must equal 180 degrees. And in that algebra, we can solve for the value of C, which would end up being 74 degrees from that equation. Right. Lastly, we got to find the measure of variable D, and we can do that again by looking at these highlighted portions. The ones that matter here would be D and A. We could also technically look at the linear pair here with 58 and D, but I want to review this specific angle pair with you guys. So if I draw these separate, what I've highlighted here would look like this. We have our variable D. We've already solved for A prior. It's 58 degrees. These are consecutive interior angles. On parallel lines, consecutive interior angles are supplementary. They have to add together to equal 180 degrees. So D and 58 have to add up to equal 180. Just like the linear pair there, D and 58 have to add up to 180 degrees. If you subtract that 58 from both sides, you're going to get 122 degrees for D in this example. Example 31, we have a triangle congruency proof. We have some given information that's not marked on our figure, so we're going to go ahead and mark it. We have RT congruent to RV. We have the angle TRS, this angle, congruent to angle VRS, which is this angle. And we're being asked to prove that RST, this angle over here, is congruent to RSV, this angle over here, where my red dots are. In order to do that, we're first going to have to prove that the triangles are congruent. So let's see how that's done. Notice we have our given stuff split into two different steps, so that means we're going to separate these two as we copy them in our proof. So we can start with RT being congruent to RV, and then we can follow that up with the measure of angle TRS being equal to the measure of angle VRS. Notice the next statement is almost the same exact thing. This says TRS equals VRS, this says TRS is congruent to VRS. That's just because any things that are equal are congruent to each other. That's the definition of equality of congruency. It doesn't really matter to me which one you put there. Next, it says that RS is congruent to RS. Let's first see the evidence of that in our figure. Notice both triangles, this one and this one, have a side RS. It's a shared side by both. We're responsible for knowing that that is congruent sides for both triangles. We call that specifically the reflexive property. Anytime we say something is congruent to itself, we are using the reflexive property. Hopefully you can tell now with the markings that are on our triangles that those are congruent by the side angle side theorem. That's important because that's what's coming up next in our proof. I can now say that triangle RST, the one on the top, is congruent to triangle RSV, one on the bottom, because of the side angle side congruency theorem. All right, and here's the thing that students have a hard time remembering. If I ever prove that triangles are congruent, which I already have, and I state after the fact that any pieces of those triangles are congruent to each other, which is what we're being asked to do in this. We're being asked to prove that this angle is congruent to this one. Well, we know it's true because we already proved the triangles are congruent. These are now corresponding angles of things that are congruent, so they have to be congruent themselves. We have an acronym for this. Corresponding parts of congruent triangles are congruent. CPCTC in this proof. In 32, we're reviewing a composition of transformations again. Here we have our pre-image segment CD, and we're asked first to translate it with the rule of x minus 5 and y plus 1. So remember, translation is a slide. That x minus 5 is telling me to go in the negative direction on the x-axis. That is going to the left. So that means go left 5. That y plus 1 is telling me to go in the positive direction on the y-axis. That's going up. So that y plus 1 means go up 1. We're going to do this with each individual point, starting with C. Left 1, 2, 3, 4, 5, up 1. Ends up right here at negative 1, positive 2. There's C prime. Same thing with D. Left 1, 2, 3, 4, 5, up 1. I'm here at negative 3, positive 6 for point D prime. We can connect those. There's our first image after the translation. Next, we are being asked to rotate this thing 270 degrees clockwise. I've made a little duplicate graph here so we can see how that works, right? So clockwise 270. I can rotate. Clockwise, again, is going to the right. It's steering your car to the right. I'm going to right turn 90 degrees. I'm going to keep going to the right another 90 degrees, that's 180. I'm going to go to the right again, another 90 degrees, that's 270 degrees clockwise. And we can see now where our segment should be located after that rotation. So C prime has ended up from the origin left 2 and down 1. We can come to our graph and graph that from the origin left 2 down 1. This is where C double prime must be located. Do the same thing with D prime. From the origin, that's left 6 down 3. So from the origin, we go left 6 down 3, and that is the location of D double prime for this composition of transformations. So again, we've rotated by hand to find our image. We can also do that thing by function notation. You can absolutely memorize the rules for function notation for rotating 270 degrees clockwise, right? C prime was at negative 1, positive 2, and it ended up at negative 2, negative 1. So what happened there is the x and y switched places, right? The 1s and 2s split places. That negative 1 remained a negative 1. The negative 1 positive, it'd be better if I show you this coordinate out here. So C prime was at negative 1, positive 2. It ended up at C double prime, which is at negative 2, negative 1. And again, we can evaluate what happened here. The 1s and 2s switched places. That original x coordinate, though, stayed negative. It's the y coordinate that came up front and changed its sign. So our function notation here would be making that negative. You can memorize function notation and just say, okay, I'm going to flip my coordinates and my y is going to change signs. It's kind of hard to remember that, though, for all of the different types of transformations and their given rules. Probably going to be good for you to know how to do it by hand like I did here. Another composition of transformations here, we need to first rotate this figure 180 degrees. And again, there's function notation rule here, which just says we need to change the coordinate signs. So our x, if it was positive, would become negative, or same thing with our y. So this negative 1, positive 2 would become positive 1, negative 2. You can memorize that function notation, or you can just do it by hand, which I'm going to show you how to do here. With this, I'm going to rotate 90 degrees. Doesn't matter which way I go, because after 180, I'm going to be upside down, and that shows me where my coordinates should be. So point A from the origin is right 4, down 3. So I'm going to memorize that. I'm going to go right 4, down 3, and graph my A prime. Point B is to the right 2 and up 2, so right 2 and up 2. There is B prime. C prime is right 1, down 2, so I'm going to go right 1, down 2. There is C prime. That's rotating by hand. You can physically turn your paper, figure out how far they are from the origin, turn your paper back, and then graph them. That's my first image. Next, I need to reflect over the y-axis. So I'm going to make my y-axis stick out. That is this line right here, my blue on the screen. And I'm taking my points and flipping them the same distance to the other side of the line. So start with A prime. I'm just going to count how far away it is. 1, 2, 3, 4. So the reflection should also be 1, 2, 3, 4 units directly across the other side. And so that would give me A double prime right here at -4, -3. We do that for each point. B is 1, 2 away, so my image is going to be 1, 2 away to the other side right here. B double prime, and C prime is only 1 away. C double prime will only be 1 away right there. Remember, it's very common for transformations to overlap like these do. That is this composition done. We have another construction here, which is copying angles. So I need to make an angle that's exactly the same as this one, congruent, same amount of degrees. That starts by first drawing a, well, it could be, depending on the rules here that you follow. It could start with just drawing a new point as a new vertex for your new angle, or that could be drawing a ray with an endpoint on it as a new side for your given angle. Right? Either of those is fine for your first step. What you would do next is take your compass, go here to the vertex of your original angle, and just draw an arc that goes through that original angle. And you would be taking the same measurement on your compass and doing the same arc going through your side. Just notice here as I do it that I'm going to be making it clearly longer than that original arc so that I have room to put my new side through this. What I'm going to do next is take the intersections here and measure them essentially with my compass, the distance between the two. Be about like that. I'm going to take that same setting and I'm going to carry it over here and make an arc intersecting right there. And all I would have to do to copy this angle is connect my vertex through that intersection and I would have congruent angles. Right? Forgive me if it doesn't look exactly perfect because my tools are wonky here on the screen. I'm going to show you that one more time with this one. Again, I can start by either drawing a new vertex, and make this one stick out by the way so we can measure well, or I can start by just drawing a new side of my angle like so. I would next take my compass and I would be drawing an arc all the way through. Keeping this same setting, I would come down here to my new vertex and again draw an arc just like it. Then I'm measuring the distance between these two intersections right here, which is about the same setting that I have. I'm carrying that over here, putting an arc through. And again, the last thing I have to do is connect that intersection to my vertex, and I get a congruent angle, right? The next example, by the way, 35 is asking for the same thing. Again, making congruent angles would be all the same steps. The one after this though, example 36, we're being asked to bisect an angle. Let me zoom in here because I can do this all on this. So what we're doing now is we're cutting an angle in half. Here are our steps. We're opening up our compass with our compass on point B, and we're going to be drawing an arc through our angle. Oops, let me make sure I get this setting right here. Gonna draw an arc through our angle, like so. Very similar to what we did with copying an angle. Now I have two intersections. I'm going to be taking my compass, placing it on one intersection, so where this arc intersects my sides, and I'm going to come out here into open space, and I'm going to make an arc like that in the middle section. I'm going to do the same thing from this intersection. Compass there on that intersection, and then again out here in space, I'm making an arc. And then where those intersect, we are going to connect that location back to our vertex with a straight line. And again, it's not really perfect because of my tools, but this segment here would be cutting this angle in half. I'm going to show you that one more time with this one. Again, compass goes on the vertex. We draw an angle through the, compass on the vertex. We draw an arc through our angle. Then we're taking our compass and putting it on each intersection and making arcs out in open space. So if I go here, I can come out here into open space with an arc. Same exact setting to the other intersection with an arc. And then again, the intersection of those arcs would get connected back to our vertex, like so, cutting our angle in half, bisecting our angle. In examples 37 and 38, we're being asked to identify if a triangle is scalene, isosceles, or equilateral. So we're classifying here. These require us to know how long sides are, because in an equilateral, all the sides will be the same. In an isosceles, 2 sides will be the same. In a scalene, none of the sides will be the same. The way that we determine that when a triangle is graphed is by using the distance formula on our sides. So I'm going to start with side AB. I'm going to stay organized. I need to know the location of A. It's at -2, +5. I need the location of B. It's at +3, -3. And those values are going to go into our distance formula, right? We labeled, we're plugging in, and we're solving. 3 minus -2 squared plus -3 minus 5 squared. That's x2 minus x1 squared plus y2 minus y1 squared with our values plugged in. Order of operations, we need to do parentheses first. 3 minus -2 is +5. -3 minus 5 is -8. 5 squared is 25. -8 squared is 64. We add those together, we get the square root of 89 as our exact value. I'm going to go ahead and label that here on our graph. Side AB is the square root of 89. We would repeat this process for the other sides of our triangle. For the sake of the time in this already incredibly long video, I'm not going to show the work on screen. Just know it would be the same as this, but for side AC, I would use point A and the location of C in the distance formula to determine out how long that side is. If I do the math correctly there, I would get the square root of 40 for side AC. And again, I would repeat the same thing for side BC. Let me make sure that it's clear what I'm telling you to do here. To find the length of this side, BC, we will follow this same process here with organization. I'll say BC. I'll say, okay, point B is located at +3, -3. Point C is located at -4, -1. I would label them, I would plug them into the distance formula and figure out how long that side is. If I do that correctly, I'm going to get the square root of 53 for side BC. And these values tell me that none of these sides are congruent. They're all different lengths. Therefore, this triangle is a scalene triangle. In our next example, we have similar stuff going on. In this one, though, we can easily count one side, so we don't need the distance formula for that one. Let me get the vertices labeled here for you. That's point A, that's point B, that's point C. Side AB can be counted easily, 6 units long. The side AC and BC, though, are diagonal. We would have to use the distance formula on those. If I do that on side AC, let's see, I'm going to get the square root of 34 for the length of that side. For BC, I would get the same square root of 34. That gives me 2 congruent sides. Therefore, this is an isosceles triangle.